Welcome to the last seminar in this year and in this semester. And it is my pleasure and honor to introduce Jindřich Libovický to his talk, Multilingual Pre-trained Encoders. We heard some more general information about this topic in Jindřich's previous talk this fall, but this will be a very focused, very elaborate lecture. So the floor is yours. Thank you.
Thanks for the introduction. Yeah, I'm going to talk about multilingual pre-trained encoders. One of the reasons why I'm going to talk about them now is because it's probably the last time point where someone cares about encoder models, because you know everyone is using those generative decoder on the models. So this is probably the last chance to talk about what we've did this year and the year before everyone forgets that pre-trained encoders ever existed. So multilingual pre-trained encoders are tools used for multilingual NLP, and the two tasks or two setups where we typically use them are cross-lingual transfer, when we have data or in general a model that can do something in a high resource language, and we would like to do the same stuff in a less resourced language, typically without having access to training data in a less resourced language. And a classical way we did that before these encoders existed, and actually the deep learning revolution in 2016 didn't change much about this, was that we could use machine translation to translate a less resource language into English or related high resource language, do the task in English, and perhaps use a model that's adapted to mistakes that machine translation models do, and then depending on what the task is, typically translate back to the low resource language. And one problem is that by doing so, we lose a broader context, because the models are trained in English, which includes the cultural context of English speakers. And the second problem is that whenever we do pipeline like this, the errors in the individual pipeline steps just accumulate. And cross-lingual NLP is not just cross-lingual transfer. There are also tasks where we have input in one language, but we are interested in output in another language. So it could be something like cross-lingual question answering or cross-lingual summarization. And in such setups, we can use machine translation in the same way as when doing cross-lingual transfer, and it has similar advantages and disadvantages. But in 2019, the thing that changed was that pre-trained multilingual encoders appeared, and the promise of these encoders was that we have a backbone model that knows all the languages, whatever that means, and we can train the model in English, and sort of for free, the model will know all the languages just based on the English training data. As we will see shortly, it's not that great as the promise from 2019 was, but well, it does something. And this brings me to the two topics of this talk. The first one is our attempts to improve multilingual encoders without using parallel data. And the second part will be about exploring moral and political values in multilingual encoders. When I say multilingual encoder, I typically mean a model that resembles the original bird. So unlike machine translation models that have an encoder and a decoder, It is encoder-only model, and its purpose is not to generate anything. Its purpose is to learn a representation of the input tokens. And the typical way it is done is using masked language modeling when we mask input tokens during training and we want to predict what tokens were masked, or there are also some more elaborate ways like a more generated discriminator setup with Electra training and so on, but typically it's based on corrupting somehow the input, and we want to figure out what was the original input before it was corrupted. And it's happening within the fine-tune and pre-train and fine-tune paradigm, where we first pre-train large model on large data. It takes a long time. And then we have some task-specific data, which is relatively small. In this case, it's typically in English. And we are training for a task-specific objective. But in the specific case of the multilingual models, during the fine-tuning, the training data is typically in high-resource language, and the test data is typically in low-resource language, or as you will see later, not always in low-resource language, but at least in a different language that was the training language. And one important property is that most of the commonly used multilingual encoders are trained on monolingual data only, and the great advantage of doing so, we just concatenate the data in all languages that we have and pretend it's just all the same kind of data and run the training. And what I would hope for is that, well, nothing gets so-called lost in translation, because we keep the cultural context of the languages, the context the original text actually appeared in, and we don't force some alignment with English using parallel data, because, well, if you look at parallel data, a large part of parallel data, especially for less resourced languages, are movie subtitles based on American movies. But the harsh reality is that it actually works still pretty badly for low resource languages. It works decently well for high resource languages, but well, with high resource languages, there's no such a problem with task specific data. But it's not that bad. It's doing something. So these are multilingual encoders, and now to our attempts to improve the representations with monolingual data only, because, well, there are clearly some limitations, and we wanted to improve the cross-lingual performance without parallel data, because parallel data for us means introducing or forcing everything to look like English. And actually, this effort started already in 2020, when we had a first paper on analyzing what new models like multilingual BERT and XML Roberta can do. It was in Findings of EMLP 2020, and in that paper we showed some stuff that we thought was fascinating. One of them was that when we took the average embeddings of sentences in different languages and then clustered the averages, it appeared that we could reconstruct partially the general genealogical tree of the languages. Well, this is a 2D projection, so it doesn't look that great as when we actually compare the trees. And we also made some bold claims about the embeddings having a language-specific component, or language ID component, and language neutral component. We we just subtracted the language specific mean from the embeddings, and it seemed that everything improves. So we boldly claim that we are making the embeddings language agnostic by just doing some very simple normalization. The preprint paper now has 150 citations, and I think that many, or perhaps most, of the bold claims we made in the paper are false. So and I will get to it during this talk. So that was well, a prehistory of this, because it's already 2020. Who cares about 2020 now? And this is one thing we have tried. We've had this in findings of ACL 2022, a joint work with Kati Hemmel, a PhD student from Munich that I co-supervised with Alex Fraser. And the idea was that we can use we can use word embeddings to improve the language neutrality of the contextual embeddings. And the motivation was that, well, we can do pretty good word embeddings with much less data than we can do than we need for training the encoders. And there are pretty decent algorithms for aligning the word embeddings, which are unsupervised. So what we did is that we started with XMLR, and in one set of experiments we derived word embeddings from XMLR, and then we did unsupervised word embedding alignment of the embeddings from XMLR. And this way of creating the word embeddings is actually mimicking the famous word-to-vec way of preparing word embeddings. It sort of mimics the continuous back of word model, and the goal, it's training a linear projection that from word embedding should predict an embedding of a sentence where the word appears. Whereas in the continuous backup words model, you use the word embedding to predict the sum of word embeddings of words which are in a context window with this model. So this is the pretty similar things. We use this expectation maximization algorithm to align the embeddings and end up with word embeddings that are better aligned across languages. And in a second step, we use the already better aligned word embeddings, which are from the same representation space as XMLR, to update the encoder itself. We experiment with different loss functions, and well, we get some results. These are results on the word embedding, quality, and this is bilingual dictionary induction. So the task is that we have the word embeddings in 2 languages, and we should produce a bilingual dictionary. And it appears that aligning the word embeddings from XMLR works actually better than aligning word embeddings from fast text. It's comparable with what was at the time the state of the art. It was the Muse algorithm by Facebook, and it's worse than using supervised dictionaries to the test data is like 50,000 dictionary items, and this is by using like 100 word paths as training data. So even this small amount of supervised data leads to a huge improvement compared to the unsupervised methods. And here, this is cross-lingual word similarity from similar 2017, and well, here, basically all the methods are similar. But already here we can see that supervised is much better. So this is what I will keep repeating all the time today, that even small amount of parallel data improves stuff a lot, and I'm starting to doubt whether it is a good design decision trying to avoid using parallel data at any cost. But otherwise we can in this way we were able to get pretty decent word embeddings, and the advantage was that we could get them for quite a lot of languages, surprisingly compared to fast text, because XML already covers 100 languages, and some of them are pretty low resource, and being inside XMLR actually helped the word embeddings compared to training with fast text directly, which was a small surprise. But well, our main goal was improving the contextual representation. Our goal was to improving this XMLR, and these are some standard tasks that people use to evaluate the cross-lingual transfer. These two tasks are question answering. This SpanX task is name entity recognition. This is part of speech tagging on universal dependencies, and this is cross-lingual sentence retrieval. And well, when I look at the numbers at the screen, it looked much less clumsy than when I see it on such a large slide. But the main message is that using the word embeddings with deep canonical correlation analysis as a loss function improves quite a lot compared to the original XMLR in most of the tasks. Sometimes it is better to use fast text embedding. Sometimes it is better to use the embeddings that we produced. And it was a bit surprising for me that using the mean squared error wasn't that good idea, because well, with the static embeddings from the multilingual encoder, we have embeddings that sort of share the representation space with the original XMLR. So using mean squared error might be a good choice. But this this canonical correlation analysis is sort of weaker loss function, because we don't force the model to replicate exactly the numbers that are predicted by the model. What we actually want when doing CCA is that we want the two spaces to end up in such a way that there exists a projection, and in this projection, these two are as correlated as possible. And it appeared this is the good loss function for this. And well, the main purpose of this exercise was that we hoped for improvements in low resource languages, and we did a reasonable improvement on average, but the improvements were mostly in high resourced languages. This paper is again joined with Kati Hemmel, Alina Fastovsky from Technical University in Munich, me and Alex Fraser, and this paper is this sort of negation of this 2020 paper I was talking about. It that we weren't that right as I thought, and the reason is that if you plot the averages of of the individual dimensions of the embeddings in XMLR, you immediately see that there are some outliers, and when you do any type of distance between these vectors, those outliers, those dimensions that are always that have always high number, make a large part of the cosine distance or the Euclidean distance. And well, what we actually did by this seemingly clever centering of the representation was that we just got rid of those outlier dimensions because they are everywhere. Some outlier dimensions are language specific, and by doing this, these language specific averages, basically the only thing we did was getting rid of those outliers. And if you look at the performance on sentence representation, if you start with vanilla XMLR and remove the greatest outliers, you can see that every time you remove an outlier, the cross-lingual sentence retrieval accuracy improves. And when we remove 18 most outlier dimensions, it's already better than doing the language specific averaging that we did. And this is comparison with multilingual sentence bed. And multilingual sentence bed was trained using from XMLR, using just a small amount of parallel data. And again, using just a small amount of parallel data improves a lot. And well, we didn't stop by removing the outliers by just deleting them. We also tried some other tricks from linear algebra, and this method is particularly interesting, or perhaps it's not interesting, but I just like it. And it's called cluster-based isotropy enhancement. What this method does is that it first does a k-means clustering to actually much more clusters than is the number of languages, and then it takes each of the clusters. It does PCA in each of the clusters and removes the first principal component. So intuitively, what it does is that it takes like those specific regions that you have in the embedding spaces and removes the stuff that makes that makes those regions special. And after doing so, well, the one thing is that you can see that the embedding spaces are suddenly much more interleaved and much more mixed. And the other thing is that it significantly improves both the cross-lingual sentence retrieval, and this STS stands for, well, one S is semantic and the second S is similarity. But the data set consists of sentence pairs in different languages, and for each of the sentence pair you have several numbers from annotators saying how similar they thought the sentences were. And well, doing this linear algebra trick improves the cross-lingual retrieval much more than removing the outlier dimensions, which in proxy means much more than doing this language-specific centering. And the other trick is called whitening, and is a pretty standard thing from linear algebra, and that is finding such a projection of the data that the data has zero mean, and the covariance matrix is an identity matrix. And by the way, those tricks, this cluster-based isotropy enhancement, and the whitening, it also improves the multilingual sentence bed, the model that was trained using parallel data. And of course, it's not only us who tried using monolingual data only to improve the multilingual encoders. The most successful work on this topic is the work of Jonas Pfeiffer, which includes using adapters in the transformer layers, and also pretty recent work by Meta showed that if they prepare the vocabulary of such a model in a clever way, they also can get pretty reasonable improvements. But besides those, there is a lot of literature showing that using parallel data, small amount of parallel data is enough, can greatly help in all those tasks. So this was the part of what we tried to do with monolingual data only. And now some analysis of the encoders when we searched for moral values, and then also for some political values. This is based on a paper that we have in Findings of ACL this year, and there were plenty of people involved. Again, there was Kati Hemmel from LMU in Munich, Björn Diesenroth from Aleph Alpha in Heidelberg, Patrick Schramovsky from Darmstadt, me, Konstantin Rotkopf from DFKI, Deutsches Forschungsinstitut für Künstliche Intelligenz, Alex Fraser, and Christian Kersting from Darmstadt. And the paper is on searching for moral values in the pre-trained representations. And we have taken pretty interesting, almost unsupervised methodology from a previous work of folks from Darmstadt, and it is based on some templates that we populate with verbs. So the templates look like: is it good to smile at people? Is it all right to smile at people? And so on. And well, the purpose of the templates is that they put the verb in relation to moral intuitions, asking if something is good or bad, and we also automatically translated the sentences into Czech, German, Modern Standard Arabic, and Mandarin Chinese. And we took the representations from monolingual models and from XMLR, and then we do PCA and take the first principal component, which then corresponds to moral sentiment according to the model. Now, you certainly ask why the first principal component of averaging some vectors should do this. And the reason is that the templates are chosen such that there is no linguistic variability within the sentences. When you do something like PCA what you get from the representations, you find out that the first principal components are something like being a noun or something like that. Most of the components have some linguistic interpretation, but here all the sentences are same. The only thing they differ in are the verbs, and also there might be some weird connotations and so on. So this is why we use multiple templates per each of the verbs, and we get the average over the template set. So the linguistic variability, even within these templates, just average out in the embedding space. And well, when we take a list of several hundred verbs, run this machinery, we already get something, and on average, it seems reasonable. Like killing killing is bad, and thanking someone is good. Well, what else would you expect? There are also some promising things that would make you think, oh, this really captures some cultural differences, because you can see that getting divorced in Arabic is worse than in other languages. But then you start up with some weird stuff like why is stealing in Czech good, or why is polluting in Arabic good? And if you look at more verbs, well, you can see that the general trend is fine, but there are plenty of outliers which are difficult to explain. So instead of looking at plots of some random words, we tried to do some more rigorous quantitative analysis. And the first thing that we observe is that multilingual models have much larger variance than monolingual models, which might be due to cultural differences, it might not. And the other thing we did is that we tried to correlate the numbers that we get with a survey done using Mechanical Turk in English, but in Germany and the USA. And the people were asked questions like, is activity something moral? And the moral and the activities were like smiling at friends, traveling to Africa, like some random phrases that some people came up with. And the results show that there is a pretty high correlation of what we get using this almost unsupervised method. And the survey, there are some outliers. This is particularly monolingual Arabic and Arabic in Czech and the multilingual model. And also we can see some differences between the languages. This plot might be quite hard to understand. So what is below the diagonal, it shows how the languages correlate with each other in the multilingual model. The numbers above the diagonal, they show how the languages correlate with each other when the moral values are taken from the monolingual model. And the numbers on the diagonal, they show how the same language correlates with the numbers extracted from a multilingual and from the monolingual model. And well, the obvious outlier is that Czech is most dissimilar from Arabic in the multilingual data, and you might start thinking immediately, well, it must be because we eat so much pork and they don't eat pork or whatever. No, the reason is that Czech and Arabic has much less training data in XMLR, and because of that, the languages are much less represented in the data and in the model, and the embeddings are pretty much random. And then you can see it even from comparing that monolingual Czech and Arabic have much higher correlation than there's in a multilingual model. And I didn't say an important thing, which is all these models are not the usual birds that produce the contextual embeddings of tokens. All these models are these so-called sentence birds. Sentence bird is a fine-tuned bird model to produce one vector per sentence, so that the one vector captures the entire sentence. And before, there was no multilingual sentence bird that was not trained without parallel data. So for this week, we created multilingual sentence bird that only uses monolingual data. The monolingual sentence birds are typically trained from the standard bird by fine-tuning on natural language inference. So we translated the natural language inference data into all the languages. Actually, there exists pretty decent translation of the natural language inference data into like 20 languages. So the only thing that we did, or actually that Martin did, was translating the data into Czech. And if we compare these numbers below the diagonal with the usual multilingual sentence bird that people use all the time for filtering parallel data formation translation, you can see that when we use the parallel data, everything is suddenly almost the same. You get very similar embeddings, and you lose all the differences in the moral dimension. But the question is, if having these differences is worth it or not. Because when we searched further for how these differences look like, we actually find that most of the differences are some stupid mistakes. For that we used parallel data of movie subtitles. Well, we just took a random sample. It seemed that everything were just perfect. So we selected parallel sentences where the scores differs the most. And actually, when we did it for the first time, we realized that those are sentences which are not actually parallel. So we had to do some better data filtering. And with better data filtering, we were able to get some examples where of parallel data where the sentences differ the most, or the estimated moral sentiment differs the most. And here you can, most of the cases in German are some stupid lexical translation. In German, gift is poison, but apparently the multilingual model thinks it's gift in English, so well, that's a good thing. Well, obviously, it doesn't know what erwürgen means. Neither did I. This is also a word that confuses the model a lot, because, well, gefallen, it can mean favor, but it is also a participle of the verb fallen, which means to fall. So gefallen also means fallen, including fallen soldiers, and so on. Well, this is the opposite example. It's apparently good if traitors like you. In Czech, I was hardly able to come with some regularities why the things didn't work. So all the errors seemed pretty random to me. So the conclusion from looking at the parallel data was that, well, if it works, it looks impressive, and then you would think, well, it really knows what is moral and what not, and then if you see the examples where it doesn't work, it looks really stupid. But I think this is also the case with like most of the models. When you play around with ChatGPT, it also, you are surprised how clever it is, and then it does something stupid, and you're surprised how stupid it is. Anyway, this was some random looking at data, so we wanted to do something more systematic. That something more systematic was that we have taken something that's called the moral foundation theory, and it's descriptive theory from social psychology, and well, the reason why we took is that the people from Darmstadt know some other people from Darmstadt who were working on this theory, and in this theory, the moral positions, well, it's not a prescriptive theory. The purpose of this theory is not to say what is good and what is bad. The purpose of this theory is to explain why, or try to explain why people intuitively think something is good or bad. And the proponents of the theory claim that the moral positions can be explained as combinations of several basic values. The 5 values we worked with were care, fairness, loyalty, authority, and purity. But there is no universal agreement in the community of moral foundation theory what exactly these 5 basic components should be. They know there are basic components, and they know that there is like 4 to 6 of them, but they argue what the correct definition of them is. But the good thing is, they have, for these 5 values, there exists a standardized questionnaire, which looks like a test from a magazine for teenage girls, almost. And when you fill in the questionnaire, it tells you how much you value these 5 basic values. And also the advantage of the standardized questionnaire is that there exist representative surveys in most of the languages that we worked with, and the results of these representative surveys are typically that all the 5 values have similar scores, as you will see later. In China, they put more emphasis on loyalty and authority, and liberals and left-wing oriented people value more care and fairness compared to the other 3 values. And we took the questionnaire and formulate the questions as statements, manually translated the the statements into the language we worked with, which was Arabic, Czech, German, Arabic. Hashim is not here, so I cannot thank him in person. Hashim did the Arabic translation, and Mandarin Chinese. Here you can see these high scores for loyalty, authority, and purity in Chinese, and higher values of care and fairness in Europe than in the United States. But when we compared the survey values with values that we have from either the multilingual model or the monolingual models, there is hardly any correlation between those. So yes, the models capture some very basic correlation with moral intuitions, but when we go into a more systematic framework and try to evaluate the values in the model in a more elaborate framework, we find out that according to this framework of 5 basic values, the stuff that the models think is close to random. So that was on the moral values. And because I like the methodology a lot, I tried to apply it in a different domain, or with a short paper and this year's findings of EMNLP. And I tried what happens if I use the same thing with the templates, alternating just one word, averaging the embeddings, doing the PC and taking the first principal component. What happens if we try out the country names and jobs? And I used 3 sets of templates. One set of templates basically says they come from a country. The second set of templates said being from a country is prestigious. And the third set of templates said working as some profession is prestigious. And I extracted the first principal component the same way as we did with the moral values, and then I was looking for correlations with 45 handcrafted geographical, linguistic, and political features of the countries and the gross domestic product of the countries. And the features were like if the country has access to sea, if it's landlocked, if it is part of the former Eastern Bloc, if it's part of former Soviet Union, if there are Alps, if they use Cyrillic alphabet, like stuff like that, 45 features. For the jobs, I have taken 2014 representative survey from the US on job prestige, and I took like 100 of the lowest and the most prestige jobs, and only taken those which I think exist in Europe. And in a final experiment, I took the job prestige dimension and tried to score the sentences about countries using the job prestige dimension. And the purpose of the experiment was to find out if the models connect somehow low and high profile jobs with the country of origin, because it's pretty common in many countries that some nationalities are connected with low profile jobs. And I evaluated these 4 models. This is one of the best multilingual sentence BERT models. This is this is a pretty small and fast multilingual encoder that was created by knowledge distillation. This is model by Google that's very frequently used for parallel data filtering for machine translation, and this is the multilingual sentence bird creating by monolingual data only that comes from the previous paper, and the results show that basically, regardless of just stating the country and saying if the country is prestigious or not, the main component highly correlates with splitting the countries into the former Eastern and Western bloc in Europe. These are different features from the 45, but we can group them easily to those that represent those, like, well, you know, Southern and Northern Europe does not correspond to this, but like distinguishing if a correlation with the country being the original EU 15 member, for instance, does. So some models also when you mention a country, the representation highly correlates with the gross domestic product of the country. And when you take the job prestige dimension and apply it for the distilled model, then it highly correlates also with being from Eastern or Western Europe, and therefore also with the GDP of the countries. And well, this is a pretty known fact that small models that are created by knowledge distillation carry much more biases than the teacher models. So we sort of, on one random example, we confirm that also in the case of multilingual models. And all the models can distinguish pretty well between high and low profile jobs. And well, yes, this is a very evil model. And well, these two do not use parallel data. These two do use parallel data. Well, in this particular case, it's hard to say if using and not using parallel data changes the results or not, because there are plenty of other differences between the models. And at the final experiments, I tried to explain what the differences between the countries come from, and in 3 or 4 models, the highest correlated feature was the language similarity based on the lexicon data set. For this model that only uses the monolingual data, the most explaining feature was geographical distance, but well, it's tricky how to compute a geographical distance, and the arbitrary method that I decided to use was that I measured the distance between capitals of the biggest country speaking the language. And that's it. So, well, yeah, we did some experiments with using monolingual data to improve the multilingual encoders, and but adding parallel data improves the tasks more than all the clever methods that try to avoid using parallel data. Pero data makes the representations more similar when we probe it for moral and political questions. And we show that multi-encoders know something about moral values and how Europe was split into the Eastern and Western Europe. But we found like no evidence that there will be like transferring of stereotypes from one language to other language or something like that. So that's it.